The problem statement has been taken from GATE Physics 2012 paper, and it reads as follows. In the following circuit, the voltage drop across the ideal diode in forward bias condition is 0.7 volts. The current passing through the diode is 0.5 milliamps, 1 milliamps, 1.5 milliamps or 2 milliamps. This is a multiple choice questions and we need to choose one correct answer. In this figure, you can see some physical diodes. These are available in the markets. You might have seen them in the labs. We'll be interested in seeing how to model these diodes. What is a model? See, a diode is an electronic device. It's not a straightforward device. It's a resistor. We call them active devices. So it has to be modeled if we want to use them in circuits, and we want to solve simple circuit using a simple KCL and KVL. We model them so that we can replace our devices. So what I want to do is I want to replace my diode with a combination of, let's say, voltage source, resistance, maybe some capacitance, I don't know, inductance and whatnot. So we'll ignore L and C for now. We'll just see that whether this simple humble diode, can it be expressed in terms of just say, let's say, voltage sources and some resistances, so that we can simply apply our KCL and KVL. This exercise is what we refer to as modeling. And this you will see across, not just for junction diodes. You must have seen this in BJTs, small signal equivalence, FETs, field emission transistors and whatnot. So a very simplistic model is shown here. This is an ideal diode. This is a diode. So it's operating as a switch. When you apply a forward bias, switch is closed and an infinite amount of current can flow. When it's reverse biased, so which is shown here, you can see the polarity has been reversed, the switch is open and no amount of current can flow, which is shown here using zero current, the horizontal line. Now what this means is that even for a very small voltage, let's say you apply 0.1 volts, you can get a huge amount of current and thus a huge amount of power. This is not realistic. However, this model, what I call as a semi-real or semi-ideal diode, what happens is that it's equivalent, it's taken forward from this. So this is, let's say, first generation, gen 1, and this is gen 2. So what is the modification that we have done? We have said that it will conduct, this diode will conduct only after a voltage of 0.7 volts. You can see a line rising here. This is what we sometimes we refer to as knee voltage. On the reverse side, this is the same as this. So if you apply a VD of negative, you can see the polarity has been reversed, no current will flow. So effectively what we have transformed this circuit to this or this, depending on the polarity. This is what I refer to as when I say we can model this somehow. So we have replaced this unknown black box using a simple switch and a voltage source. What I call as semi-real or semi-ideal is not the true picture. This will give you a true picture. So we have forward operating region, we have a drop voltage, and we have a leakage current, and then it breaks down at a certain voltage, which is called reverse breakdown voltage. But we'll stick to this model, the semi-real model, because the question itself says that a drop of 0.7 volts is there across the ideal diode. This was the problem. Now we have seen that we can replace this diode with some known circuit elements. So let's do that. So this will remain 24 volts. This is a power supply, and this resistance will again remain the same. This is the node, and now I'm replacing this with what did we saw in the forward bias. It's a switch and a voltage source of 0.7 volts. Correct? This is what we saw there. This resistance will remain the same as 6K, and let's complete the circuit diagram. I am assuming this to be the ground. The current flowing here would be ID. Okay, and let's assume a current of I is flowing through this branch and a current I1 flows through here, and let's simply apply KCL on this node. So incoming current will be equal to outgoing current. So incoming current, we have capital I. This should be equal to outgoing current. This has two branches, I1 plus ID. Very good. Now let's calculate the value of I in terms of, and let's assume this node has voltage V, this specific node. Okay, so let's apply Ohm's law across this resistor. We will get 24 minus V. This is the voltage drop across this resistor. This point is 24, this is V. 24 minus V equal to I. Current through this resistor is I into 12K. So we'll get I equal to 24 minus V over 12K. Now apply Ohm's law across this resistor. We'll get V minus 0 equal to I1 into 6K. So I1, we got V over 6K. Again, this point is at V, and so this point will be at V minus 0.7 because there's a 0.7 volts drop across this voltage source. We'll do that. Ohm's law across this resistor will give us V minus 0.7 minus 0. See, this node is V minus 0.7, this node is 0. This should be equal to current. Current through this resistor is ID times 3.3K. So ID has come out to be V minus 0.7 over 3.3K. Now we have the expression for I, I1 and ID. Let's put all these three in this expression. So I'm rewriting this here. I equal to I1 plus ID. So I is 24 minus V over 12K. I1 is V over 6K plus ID is V minus 0.7 over 3.3K. So K will get cancelled, and you can also cancel the term 3. 3 is common in all these denominators. So we'll get 24 minus V over 4 equal to V over 2 plus V minus 0.7 over 1.1. I simply took 3K common from both sides from the denominator. Now let's shift V terms on the right hand side and constants on the left hand side. So we'll get what do we get? So we'll get 24 by 4 plus 0.7 by 1.1 equal to, we'll get V by 4 plus V by 2 plus V by 1.1. Let's solve the LHS first. So we'll get 6 plus 0.7 over 1.1. This is 3V by 4. V by 4 plus V by 2 is 3V by 4 plus V over 1.1. We'll get 6.6 plus 0.7, that's 7.3 over 1.1 equal to, let's take the LCM here. So that will be 3.3V plus 4V over 4 times 1.1. This will give 7.3 over 1.1 equal to 7.3V over 4 times 1.1. So 7.3 gets cancelled, 1.1 gets cancelled. We get V equal to 4 volts. Okay, very good. Now we were required to find the current through the diode. So we know the diode expression, it was somewhere. It was, so it was here. So let's put this value of V here. So this would be ID 4 minus 0.7 over 3.3K. That would be 3.3 over 3.3K. This would be 1 milliamp. So we have calculated the value of ID as 1 milliamps. Let's go back to our question. Okay, so this was an option. So our correct option is B, 1 milliamps. Thank you for listening.